Hello. The purpose of this video is to cover material that we would have discussed had a class been held on Wednesday, February the 13th. There was no class then due to closure of the school following a major snowstorm. In a previous class, it was right at the end of that class that we briefly talked about an important concept that's found at the beginning of chapter 17, namely pi electron delocalization. I had originally planned to complete chapter 17, but I changed my mind. Instead, we'll cover a different chapter, actually a special topics chapter that per se is not a separate chapter in our textbook. The remaining chemistry in chapter 17 is diverse and somewhat lengthy, and I think it's best to discuss it as part of the material for exam 2 down the road. The material in the special topics chapter is shorter and more closely related to previously studied concepts. Well, what is this special topic? It is this: organometallic compounds. What's an organometallic compound? Well, it's one whose molecule has a direct bond between carbon and a metal. The carbon-metal bond is always polar, with a carbon negative and metal positive because of the greater electronegativity of carbon versus a metal. Now there's a wide range in the degree of this polarity as the metal varies. With metals of relatively high electronegativity, for example lead, copper, cadmium, mercury, the bond is predominantly covalent with a moderate degree of ionic character. With metals of relatively low electronegativity, example sodium, potassium, the bond is essentially 100% ionic in character. With metals such as lithium or magnesium, these are slightly higher. These have slightly higher electronegativity than sodium, but lower electronegativity than lead or mercury. The bond is predominantly ionic with some covalent character. At the bottom of the slide are some examples of organometallic compounds. This sodium propionide. Notice there's a bond between sodium and carbon, but it's essentially a 100% ionic bond. This compound we would have seen, or we did see, last semester. The second compound is called tetraethyl lead. It was a compound that used to be added routinely to gasoline to improve its burning characteristics in an internal combustion engine. It's no longer used. It proved to be a contaminant to the environment. Instead, they have found certain organic compounds that achieve the same basic purpose. The third compound is an organometallic. It has a mercury carbon bond. It's called mercurochrome. It's an antiseptic and an antibacterial that was routinely used for cuts and scrapes, other wounds. I don't think it's used anymore, though, although it might be used in Europe. Now, it's important to understand the difference between a true organometallic compound and a compound that might happen to have both metal and an organic component to it. A true organometallic compound is one whose molecule has at least one bond between carbon and a metal. The compounds that we show here have both metal and an organic part to it, but they are not true organometallics. There's not a direct bond between metal and a carbon. Both these compounds are organic salts with a metal cation. The real value of organometallic compounds is they have proven to be very useful in synthesis applications. Now you can see in the title, we next see on the slide, preparation of organometallic compounds. Well, I'm going to defer that till later. What I want to do now is actually focus on the chemistry of organometallic compounds, and then later we'll talk about ways to prepare them. Alright, so the focus now is on the reactions of organometallic compounds. The carbon portion of the organometallic compound is a carbanion or carbanion-like component. When it acts chemically, an organometallic species basically delivers a carbanion. Carbanion is a carbon with a pair of electrons and has a -1 charge. Alright, now the carbanion, the component of an organometallic, chemically behaves in two possible ways, as a strong base or a nucleophile. Let's first look at the carbanion as a base. Well, carbanions are very strong bases. In fact, they're nature's strongest known bases. An alkyl carbanion has a Kb of about 10 to the 36. That's a huge number, meaning that the base is very, very strong. Well, the carbanion, being a very strong base, would have a very strong compulsion to accept a hydrogen ion from an acid, even a very weak acid. Let's take a look. These two reactions here are instances of a reaction of an organometallic, here this organomagnesium, here the organolithium. The reaction of each of these with a species that is known to be an acid, but very weak acid. So if we take our organomagnesium, mix it with an alcohol, there is a favorable and spontaneous reaction, even though the alcohol is a very weak base. The carbanion component of the organometallic is such a strong base that it will successfully pluck off the hydrogen ion from the alcohol. The acid-base reaction ensues. Now, another way to show that this reaction is favorable goes back to the concepts that we talked about in Chapter 3. If you recall, to decide if an acid-base reaction occurs favorably from left to right, you write an equation for that, and that's what we have here. On the left side, acid reacting with base to produce the products on the right side. Well, such an equation on one side will have an acid, and of course the alcohol is the acid here, and the products of that potentially could react in reverse, and that reaction is also an acid-base reaction. So on the right side, what we need to do is to look for and find the species that behaves as an acid in this reverse reaction, and that would be this hydrocarbon right here. If it goes looking at it going backwards, this is ethane is behaving as an acid. So on the left side, the alcohol is the acid. On the right side, ethane is the acid. If you think about what we talked about in Chapter 13, look at the notes. It will show that the alcohol is a stronger acid than an alkane. Well, the favorable direction in an acid-base reaction is to go from the stronger acid to the weaker acid. Indeed, the stronger acid is on the left and the weaker acid is on the right, so it's favorable from left to right. In the next reaction, we have a reaction between an organolithium, organometallic, and water. Of course, you all remember that water behaves both as a weak acid and, of course, also a weak base. Although it's a weak acid, the methyl carbanion component is so powerful a base, it will favorably pluck off a hydrogen ion from the water, and it will produce successfully an acid-base reaction. To see that it is successful and favorable from left to right, the acid on the left is water. The acid on the right side, imagining it to go right to left, is methane. The chapter 3 notes, if you consult those, you'll see that water is a stronger acid than a alkane. Indeed, we have the stronger acid on the left, the weaker acid on the right. This is a favorable acid-base reaction from left to right. So the point being that organometallics, the component, the carbanion component, is so powerful, so strong a base, there will be a favorable acid-base reaction even if the acid they're reacting with is very weak. All right, let's look at carbanions as nucleophiles. The general relationship, the more powerful a base, the more reactive it is as a nucleophile. All right, here we show the general overall reaction of a carbanion, the carbanion component of an organometallic, in a substitution, an SN2 substitution reaction. Here we have a substrate with a X, the leaving group, X being chlorine bromine iodine. We could also add the leaving group that we learned about earlier in chapter 13, the tosylate, the OTS. Well, the carbanion, you can see, will act as a nucleophile here, bonding to the carbon, the electrophilic carbon, pushing off the leaving group, leaving with its pair of electrons, and we're always going to see it in an SN2 type reaction, SN2. This is the overview of the type of reaction that we'll see with organometallics. Now, a second type of reaction where the organometallic component, or rather the carbanion component of the organometallic, is an addition reaction to a carbonyl group, generally of an aldehyde or ketone. In this case, well, the carbon-oxygen bond is polar with the oxygen negative and the carbon positive. When you mix it with an organometallic, the carbanion part, being negative, is electrostatically attracted to the positive carbon of the carbonyl group. The metal cation is electrostatically attracted to the negative oxygen, and an addition reaction ensues. And here is the addition product. This is indeed an important reaction, and we will talk about it in the chapter pertaining to the chemistry of aldehydes and ketones, but I don't want to focus on the details of that at this time. I believe the author of your textbook does go into it, but we're going to defer that. Indeed, this is an extremely important reaction, but stay tuned. We'll talk about that when we talk about that chapter on aldehydes and ketones. Focus now is to examine, to look more at organometallics behaving as a nucleophile in substitution reactions. Substitution reactions, in fact, on carbon. There are three general categories of substitution reactions that we're going to look at. One is a reaction of an acetylide with a carbon substrate and an SN2. Now, I'm not going to belabor that reaction. It was something that we previously studied in the first semester of organic. Just to call attention to, in fact, an example of at least the organometallic involved there, it's this. Sodium propionide, when you mix it with a substrate for an SN2 reaction, the propionide carbanion is a very strong nucleophile that will carry out an SN2 reaction on the substrate. If you check your notes, you'll see what I mean, and that reaction then hopefully is familiar. But I'm not going to say more about that. Second type of reaction, well, this involves a special kind of organometallic. It's called a Gilman reagent. And it turns out to be an active participant in a variety of important SN2 reactions with a carbon substrate. Here, this equation shows the overall reaction of what's called the Gilman reagent. The Gilman reagent has a carbon-copper bond. Actually, there's two carbon groups directly bonded to the copper. G is my symbol for a carbon group. Interestingly, if you look at this compound, there's actually two metals. The lithium is formerly a +1 charge, and the rest of it is a -1 charge. It's an interesting case where the metal itself actually has a negative charge. That's not typical. But there are two carbon groups bonded to the central copper, being negative, and then the counterion Li+. That is the general structure for what's called the Gilman reagent. When we talk about the synthesis of organometallics, we're going to, in fact, see how the Gilman reagent is prepared. If you mix this organocopper reagent, the Gilman reagent, with a carbon substrate that can participate in SN2 reactions, you do get a favorable SN2 reaction where the G group breaks off as a carbon nucleophile bonding to the carbon, pushing off the leaving group. Now the Rx that we show here, in order to achieve an SN2 reaction, must be primary or methyl. As well, it can be secondary cyclic. Now this is an interesting technicality. It can't be just any old-fashioned secondary. It can't be an open chain secondary, but it has to be secondary cyclic. But anyway, if you bring together these types of reactants, the organocopper Gilman reagent with a substrate that can undergo SN2, you get a favorable SN2 reaction. The G breaks off, bonds to the R, making this product. Now, we want to look at some specific reactions first of the Gilman reagent, and then we're going to look at another reaction of an organometallic compound, and we're going to do this in the form of exercises. So let's take a look at each one and see what the product is, and moreover I'm going to explain how you figure out what the product is. We're going to go through a step-by-step process. Alright. When your task is to figure out the product of a reaction, avoid trying to consult memory banks. Learning organic chemistry is not about memorizing reactions. Rather, the idea is to examine the reactants and determine the category of the reaction. Recall that there are 6 categories of reaction, including substitution, elimination, addition, and so on. The functional groups or agent in the reactions will indicate the reaction category. For example, when you see a double bond, think addition. If you see an oxidizing agent, the reaction will be an oxidation. The reaction here contains an organometallic compound. What you should do first is rewrite the structure of the organometallic compound. Write it in its ionic form. Here's how. First, find the metal. The metal here in question is copper. Find the carbon groups attached to it. Well, there are 2 methyl groups attached. In general, there may be 1 carbon group, there may be 2 or more. Regardless of the number of carbon groups, break off 1 carbon group and write it as a carbanion. Put a pair of dots on the carbon, make it -1 charge. So let's do that here. I'm going to break off one of the methyl groups, put a pair of electrons on the carbon, make it a -1 charge. Right, now everything else in the molecule will be positive. So the remaining portion will be CH3, Cu, Li, and the whole thing is positive. This is the ionic form of this organometallic, the lithium dimethyl cuprate, the Gilman reagent. All right, what you want to do next is examine the carbanion that you wrote. There are two possible ways that the carbanion will react. It will react either as a base or a nucleophile. To tell how it will react, examine the other reactant. Here, 1-bromo-propane. Right, there's two possibilities. The other reactant will either be an acid or a substrate with a good leaving group. If it's an acid, it could be even a weak acid, like water or alcohol. If it's a substrate, you'll find that it's methyl or primary with one of the known good leaving groups, chlorine, bromine iodine, or the OTS, the tosylate group. All right. Now in this case, we see that we have 1-bromo-propane. Is this an acid of any kind? I hope you see that it's not. Is it a substrate with a good leaving group, a primary or methyl? Well, yes, it is. It's a primary substrate. The carbon here is primary. And bromine is known to be a good leaving group. So that tells us that the methyl carbanion that we wrote will behave as a nucleophile. And this nucleophile will react with the substrate in an SN2 reaction. What I like to do is to draw a long curved arrow from the electron pair to the carbon that it's going to bond to and show the leaving group coming off. And really that's it. If you just piece that all together, that's going to give you the product. So I want to attach a methyl group to that CH2, so we'll go ahead and write that. CH3, CH2, CH2, and CH3. Now the byproducts of the reaction, in this particular case, it's a little sticky, but I think it'll still make sense. What happens is the lithium comes off as a stable Li plus and coordinates with the Br to make lithium bromide. It's one of the byproducts. If you take the lithium away, what you're left with would be a neutral copper methyl compound. Methyl copper it's called, and you just write that as CH3 Cu. All right, so here are the products for that reaction, and that's how you figure out what they are. All right, let's go ahead and look at another reaction involving an organometallic. Here we have propyl lithium reacting with ethyl alcohol. What are the products of this reaction? Well, we examine the reactants. We note that we have an organometallic, propyl lithium. The first thing we're going to do is to write that organometallic in its ionic form. There's the metal. Look for the carbon group attached. There's one carbon group, the propyl group. So we'll break off the propyl group and write it as a carbanion, putting the pair of dots on that carbon, making it -1. The remaining portion is positive. That would be the lithium Li+. So this is the ionic form of our organometallic. Now, the carbanion here Chemically, it's going to behave in two possible ways. Either it's going to act as a base or a nucleophile, and we have to decide how it's going to react, which possibility. The way to decide that is to examine the other reactant, the ethyl alcohol. Is ethyl alcohol, could that be a substrate in an SN2 reaction? Does it have a good leaving group? Well, the answer, of course, is no. No, it doesn't. So ethyl alcohol can't behave as a substrate. It has no good leaving group. That means that the carbanion cannot be a nucleophile. Well, let's examine the ethyl alcohol again. Could the ethyl alcohol, or is the ethyl alcohol an acid? Well, the answer is yes. We learned in the alcohol chapters that alcohols are weakly acidic. It's a weak acid. So you see, we have now we've found out that the carbanion is going to behave as a base reacting with the alcohol as an acid. And so let's go ahead and do that. The methyl carbanion will pick up the H plus from the alcohol. There's the transfer of hydrogen ion from the alcohol to the carbanion, and we'll just simply write the result of that. CH3, CH2, CH3. And then the remaining part, the conjugate base of the alcohol, would be the other product of this acid-base reaction. The lithium ion would carry over actually with the alkoxide ion. So these are the products of this particular reaction. Okay, here's another example of a reaction of an organometallic compound. This is a Gilman reagent. It's a little bit more complex looking. It has two isopropyl groups bonded to a central copper and then the lithium cation. This is reacting with this compound. It's called benzyl iodide. What is the product of that reaction? If you'd like to pause the video now and think it through, that could be a good thing. And the next slide we're going to go through the steps to figure out what the products are. All right. Now, when you see an organometallic compound in a reaction, the important thing is to do this first. Write that compound in its ionic form. And so I've done that here. What you do is find the central metal, here it's the copper, and look at the carbon group or groups bonded to it. There's going to be one or two or more. Regardless of the number, you're going to break off one of those carbon groups and write it as a carbanion. So there's two isopropyl groups. I'm going to break off one, put a pair of dots on that carbon, make it -1, and everything else then in that molecule would have a positive charge. This is the ionic form for that Gilman reagent. The really reactive part of this, of course, is the carbanion part. Now it's going to behave either as a base or a nucleophile. To decide which, you will look at the other reactant. If the other reactant is an acid, even weak acid, then you're going to have an acid-base reaction between the carbanion acting as a base and the other acting, of course, as an acid. If that other reactant is not an acid, look for it being a substrate in an SN2 reaction. It means it's going to be primary methyl or possibly secondary cyclic with a good leaving group. Right? The CH2 carbon here, that's a primary carbon. Iodine is a good leaving group. And we could say, this looks like a substrate in an SN2 type substitution, and well, That's we found it. That's going to be the reaction. The carbanion is going to act as a nucleophile, not a base, a nucleophile reacting with this carbon substrate. And the negative carbon is going to come over, form a bond to the CH2, and kick away the iodine leaving group. The iodine leaves with its pair of electrons to become iodide ion. And you piece all that together, attaching this isopropyl carbanion to this carbon. It would give you this compound here. It's the major organic product formed. The iodide ion that comes off coordinates with the lithium plus to make lithium iodide. And what remains is this neutral isopropyl copper compound. This really has no value. This would be the wastage. All right, I hope that's clear. Now, we come to a third type of reaction where the carbanion component acts as a nucleophile. It's a type of substitution reaction. There's some dovetailing that's going to occur here because the reaction we're going to look at is the reaction of an organometallic with an epoxide. Now, we've recently studied epoxides. You recall that the reaction of epoxides involves a ring opening addition. Pattern-wise, the thing reacting with epoxide will consist of an electrophile nucleophile. Now, when the reactant here is an organometallic, and actually what will work, there's a limitation here. The organometallic that reacts with epoxides will either be an organolithium or an organomagnesium. The organomagnesium compound shown here is in fact called a Grignard reagent. It has, the general formula is a carbon bonded to a central magnesium and then contains a halide ion. All right, well, let's look at this first reaction. Now, epoxide reaction, of course, is ring opening addition, but the rate determining step is the attack of a nucleophile on the carbon, breaking away this oxygen. And the attack of the nucleophile on the carbon, it's basically an SN2 type process, if you recall. And that's what's going to happen here. The organometallic, the organomagnesium, is going to break off a carbon anion, a carbanion. They'll act as a nucleophile, and the nucleophile will seek out and bond to the epoxide carbon, breaking away the oxygen here, breaking the CO bond. Now, all right. Now, there's consistency here. We never see an organometallic write it in the ionic form. And of course, if you write this ionic form, I don't have the tools to show you this, but this would be, you write R as R paradox negative charge, and the magnesium would be, or the rest of it would be MgX plus. The carbanion, to decide what it's going to do, if it's reacting with epoxide, it will behave as a nucleophile. The nucleophilic R bonds to the carbon, breaking the CO bond. The electrophile is the positive MgX that bonds then to the oxygen, as shown here, and the carbon nucleophile bonding to the epoxide carbon. And this is the ring opening addition product. It's a magnesium alkoxide salt. If you walked away, this would be the final product. You could put this magnesium alkoxide salt, you could in principle recover it, put it in a bottle, but generally you don't. There's a continuing theme that we're going to see in second semester where the products of reactions are some kind of an organic salt. Organic salts are very, very hard to isolate and purify, and what you normally do is further treat it in the workup process to convert the salt to a neutral organic compound. That's what we're going to do here. Going from here to here, that's the ring opening addition, but we take it one step further during this phase called the workup. In the workup, we add aqueous acid. The aqueous acid just does an acid-base reaction where the H plus bonds to the negative oxygen here. And the product that we now get, and we will go after and isolate, the useful product is a neutral alcohol product. So from the beginning to the end, the epoxide reacting with the organomagnesium, called the green reagent, it does the ring opening addition, followed by acid workup, and the final product really is alcohol. The reaction here is very similar. The only difference is that we have an organolithium compound, but the organolithium, writing it in the ionic form would be R minus, pair of dots, Li plus. You can see then there's the obvious nucleophile electrophile. It's going to break open the ring. The lithium plus hooks on to the oxygen, and the R carbanion nucleophilically bonds to that carbon, and this would be the ring opening addition product. This is a salt. We don't leave it like this. We also do an acid workup, and this acid workup, added acid H plus protonates the oxygen, negative oxygen, to give us our final product, which is a neutral alcohol. The neutral alcohol is what we would go after to isolate and purify. All right. I just have one more slide, and it's this. The reactions shown here involve symmetrical epoxide. You recall when we talked about chemistry of epoxides, epoxides can be unsymmetrical, and that's what I have here. I have an unsymmetrical epoxide reacting with an organometallic, an organomagnesium compound. All right. The organomagnesium compound, of course, like any organometallic, we write it in the ionic form. That's kind of brought forth here in that if you write in the ionic form, it's the this is actually the phenyl group that we'd write in the as a carbanion, phenyl group with a pair of dots here and a negative charge. And then this portion here would be the positive part. The MgBr would be plus. All right, and of course, writing it in ionic form, it brings forth the actual electrophile nucleophile parts of this, which you need to know when you're deciding on the ring opening addition product with the epoxide. Now the other decision to make, though, is in this unsymmetrical epoxide, which CO bond breaks. We talked about that before. Now the conditions here for when you have an organometallic, it's always going to be base/neutral, never acidic, because if it was acidic, the acid would strongly react with the organometallic and basically destroy it. So when you have an organometallic and epoxide, it's always base neutral. If it's base neutral, it's fundamentally an SN2 ring opening process. If it's SN2, that means the nucleophile, the carbon nucleophile here, is going to bond to the carbon epoxide that is sterically less hindered. And of these two, this of the two hydrogens, this has methyl hydrogen. It's the epoxide carbon here that's less sterically hindered, and so the nucleophile preferentially in an SN2 process will bond to that carbon. It'll bond to the carbon on the right, breaking this CO bond. And when you break that bond here, the MgBr plus attaches to the negative oxygen. The phenyl group nucleophile bonds to that carbon, giving you this part right here. This right here is the ring opening addition product. If you left, that would be it. If you wanted to go through the labors, you could. This is a salt, alkoxide salt. You could, in principle, recover that, but it'd be hard and also difficult to purify. So we don't. We do an acid workup, just like we did before. Adding acid, the acid provides H+, which bonds to the negative oxygen. Water actually then bonds to the magnesium, producing this magnesium salt here. This is a byproduct. We'd separate this out. And the important organic product here is an alcohol. So in general, reacting an epoxide with an organometallic gives you a ring open addition product. After the acid workup, you're going to get an alcohol as a product. And so you could say, well, this is one general way to make an alcohol, starting with an epoxide and allowing it to react with an organometallic. We want to stress that the organometallic has to be an organomagnesium or an organolithium compound. All right, that completes our discussion. In class, we'll talk about the ways to synthesize organometallic compounds. Thank you for your attention.